what we did was we used the gauge theory description to allow some non-classical configurations, and in that bigger world, the Einstein-Hilbert action wasn't well defined as a real function, but it's well defined mod 2 pi if we quantize the coupling. As I say, I can't promise it's the right thing to do, but I do believe that if 2 plus 1 dimensional gravity does make sense as a quantum theory, there's some analogous quantization of some kind that is needed. Anyway, if we take the gauge theory description literally, then both k left and k right are integers. And from the formulas of Brown and Hanel and the mapping between gravity and Chern-Simons theory, we can calculate the central charges, and their multiples 24 times integers. That's an interesting result because holomorphic factorization is possible in two-dimensional conformal field theory precisely at these values of C. Holomorphic factorization is a drastic simplification. A generic conformal field theory is a many-body system that you can't really solve. There are integrable theories that are much simpler than generic ones, but the holomorphically factorized theories are the simplest of all by far. So we're going to make the most optimistic assumption of assuming that these are the right values of C, or equivalently of K, and that the theory is holomorphically factorized. Holomorphically factorized means that there are left-moving modes. Remember, the dual conformal field theory is in two dimensions, one space, one time. Conformal invariance means that all modes travel at the speed of light. Along the line, they travel either to the left or to the right. And holomorphic factorization simply means that left-moving and right-moving modes don't scatter each other. In general, conformal invariance would allow extremely complicated phase shifts. Well, extremely complicated deformations of left and right moving waves by each other. It's very difficult to describe. So in continuing, we're going to assume holomorphic factorization. That is, we'll assume that there's a theory of left-moving waves and a separate theory of right-moving waves. They don't interact with each other, and we'll just try to describe one of them. That's a drastic simplification because we're now in one dimension instead of two. Or in Euclidean space, because our functions will now be holomorphic. So we're just trying to describe the holomorphic part of the theory, a holomorphic conformal field theory with central charge 24K for some integer K. Now, one simple fact is that the ground state of such a theory is minus C over 24, which is minus K. And that's actually the simplest way to see that C should be divisible by 24 for holomorphic factorization. The ground state energy has to be an integer if the left movers by themselves should be a good modular invariant theory. But it actually is minus C over 24, so we want C over 24 to be an integer. So it was kind of nice when we got this 24 by computing the central charge, but there was a little bit of sleight of hand involved. I won't try to explain it now, but if you wish, you can look in the paper. Okay, well, the ground state has energy minus K. What else is there apart from the ground state? Well, naively speaking, nothing, because 2 plus 1 dimensional gravity is trivial. But that isn't right. At least there are boundary excitations that lead to the Virasoro algebra of Brown and Hanel. Now, if there were no other excitations, the partition function in genus 1 would be this thing. The partition function is defined as the trace of Q to the H. So it's the sum over all energy levels. Let's say an energy level n, the number of levels of that energy times Q to the n. Q is taken to be less than 1 so that the sum converges. So the ground state had energy minus K, so its contribution is Q to the minus K. But according to Brown and Hanel, there's a Virasoro algebra, and we can act on the ground state with the Virasoro generators. So we can make more general states, for example, L minus 2 to the n, or to the a sub 2, let's say, acting on the ground state. or L minus 3 to the A sub 3 times L minus 2 to the A sub 2 acting on the ground state, and so on, we can make a product of the Osora generators acting on the ground state. That'll give an energy that'll be minus K plus 2A2 plus 3A3, and so on. Of course, to make finite energy states, we should only create states by acting with finitely many LNs for any given state. So what has been written here, I've simply written down a generating function that counts these states. So the 1 over 1 minus q squared, well, this is like a free Bose gas. The ground state energy is minus k, the excitation energies are 2 times an occupation number A2, 3 times an occupation number A3, and so on. It's a one-dimensional Bose gas, except the lowest momentum is 2. The allowed energies are 2, 3, 4, and so on. And this is simply the partition function of the free Bose gas. So what I've written is the partition function that counts all the states we know about that are close to the vacuum, and that were essentially, whose existence follows from the construction of Brown and Hanel. Now, although it's a nice function, it can't be the full answer because it's not modular invariance. Modular invariance is the special case of general coordinate invariance that exchanges the space direction and the time direction. When we go to Euclidean signature, we should be able to exchange space and time, a 90-degree relation, so to speak. And that gives what should be a symmetry of the partition function, but this particular function isn't modular invariance. So there have to be some additional states, which in the lingo means there have to be some additional primary fields other than the identity. And the partition function is not going to be the function we wrote. It'll begin that way because near the vacuum, Brown and Hanel already described all the line activations of the vacuum. So it will begin this way, but at some point there will be more states. And we're going to interpret the fact that the theory is classically trivial to mean we should make L as large as possible. As far as the near anti-de Sitter space, there was nothing except these states. We have to add something else, but we're going to push it up as far as we can. It turns out that the largest you can make L is k plus 1, and if this is the right value, then the partition function is uniquely determined. And my proposal is that this gives the partition function of the dual conformal field theory, including the black holes. Now I want to explain this statement that if L is as big as it can be, then there's a unique possible partition function. A Riemann surface of genus 1, they're parameterized by something called the J function. Well, a Riemann surface of genus 1 is made by taking a parallelogram and identifying opposite sides. And one starts with the complex number tau on the upper half plane, such that the corners of the parallelogram are at 0, 1, tau, and 1 plus tau. Modular invariance, by the way, acts like so, where A, B, D, and C are integers, and exchanges different ways of parameterizing essentially the same torus. Then it's convenient. So Riemann surfaces of genus 1 are parameterized by tau up to a modular transformation. But there's another classical way to parameterize it. We introduce Q, which is e to the 2 pi I tau. And then there's this magical function of Q, the J function, which has a simple pole at Q equals 0, and then a Laurent expansion around it. So Riemann surfaces of genus 1 are in one-to-one correspondence with values of J.